All right, welcome, functions folks. Lesson 1.5, and this lesson is a bunch of bits and pieces, not really anything that's worth a full period's worth of work, and in fact, not even a half a period's worth of work. A lot of it review we'll see, but worth paying a little bit of attention to. Some is review and very little new, but let's get through it. It'll mean hopefully short on the lesson, long on the you practicing stuff that you already sort of know anyway. But the first thing, the 3-minute review, is to talk about even and odd functions. And even and odd functions go well with polynomial functions, so it's worth talking about it again. Remember, a function is even if it's symmetric in the y-axis. If the graph is symmetric in the y-axis. That means it's kind of a flip this way. We think of the parabola, right? It's a flip this way. Bad sketch, but you get the idea. We also said that there was something algebraically that went on for even functions, and this is what we're going to test today in the 3-minute review example. It's if f at x is equal to f at minus x. So the idea is you get the same output whether you put in x or minus x, and that's what it means algebraically to have an even or symmetric function. So this is what we're going to test algebraically, and we're going to practice that again today. It's odd if, remember, the graph is symmetric over both axes, or we say through the origin. If the graph is symmetric through the origin, or we also think it's symmetric after flips in both axes. In both axes. And it's the idea if we had a piece up here, we flip it in both axes, well, down there and then down there, right? And that looks a lot like the x cubed function, right? So flip there, and that's the idea of through the origin. Any point on the graph, if I go through the origin, it's also a point on the graph. And the way we think of this algebraically is f at x is equal to negative f of negative x. And this makes sense both ways. Here, if that's x, this is minus x, but the output value isn't the same. It's the negative, the opposite output value. And I also think of it as a flip in the direction of x and a flip in the direction of y. So algebraically and geometrically, the picture and the algebra make sense. That's what an odd function means. So if I'm given a function, how do I determine whether they're even, odd, or neither? And I'd be tempted to just to bash that into a calculator and look for the symmetry, but not always is that a good plan, because it might look close to being symmetric but not. We want to use the algebra. So here we go. Here's the solution. It's, first of all, let's check out even. It's even if this is true. Well, let's see if we can prove this is true. How do we prove something is true? I'm going to try the left side and the right side, just like we did in grade 11 trigonometry. So the left side is just f at x, which is just this function. That's kind of like the goal. Can we make the right side equal that? Well, what's f at minus x? F at minus x is I take out the x, right? And that's what I've done. Whatever goes there, I've taken it out, and I'm going to fill it with whatever is in the hole there. But then I can simplify it, right? What's negative x cubed is negative x times negative x times negative x, which is minus x cubed. And what's negative x all squared? Negative x times negative x is positive x. And then, well, this I wouldn't write like this. I'm going to write minus 1 times 3 is minus 3x cubed. And that's as simple as that's going to get. Now the question is this equal to this? Well, the second part's the same, but the first part's not. Left side is not equal to the right side, So what can I say? It's not even. So that means it's not going to be symmetric in its x-axis, or y-axis rather. Well, what about odd? Let's get a different color here. Switch things up. It's odd if f at x is equal to negative f at negative x. That's the algebraic definition. I'm going to take the same approach. Left side and right side, and the left side's pretty boring. It's just the plain old function again. Now the question is can I make the right side equal to that? Well, the right side is negative f at negative x. Well, notice that this part here, that part right there, I'm going to put in square brackets, is just this over here, isn't it? Right? That's f at negative x. And instead of going through that process again, I'm just going to copy that function in there and proceed from there. Well, I've got the minus out front though, from the minus f at minus, or f minus f at minus x, the minus out front, distribute that through, multiply everything. Ah, there we go, positive 3x cubed. But notice now it messes up the second term. Right? The first term's good, the second term's not good. So the left side is not equal to the right side. And so what does that say? So y equals f at x is not odd. So what can I say? This function is neither even nor odd. And I'm hoping, I'm guessing that some of you are getting sort of a quick idea about whether a function can be even or odd just by the way the exponents work. But this is something we're practicing again today. That's a 3-minute review. On to the rest. Transformations, transforming y equals x cubed and y equals x to the exponent 4. So essentially what this is we have two new parent functions, right? We already talked about the shape of y equals x cubed. And basically we think of these points, right? And this is the snake shape. Hopefully you can remember the snake shape. And those points we graph quickly. We haven't talked about y equals x to the exponent 4, but again, we could think of this very quickly. This is going to be parabola shaped. When we're asked to graph instead of sketch, I have to be a little bit more precise. But when it's negative 2 to the exponent 4, that's positive 16. These numbers are going up very quickly. We realize that. This is why it's kind of like a boxy parabola. Still goes through, some of them, you know, they go through a lot of the same points. But the idea here is once I get this basic shape, I should be able to use what I know from grade 11 and earlier this year, transformations, to be able to graph some of these functions. So in this case, I'm going to use the parent function, y equals x to the exponent 4. And this I'm not going to write every time. This is in my brain, right? This is my thought cloud inside the brain. Got it committed to memory, or at least not scared to produce this very quickly on my own. We're asked to list the transformations. Notice that means we've got to sort of pick out each of these things and say what it does to this original parent graph. Remember, we had all those other parent functions from earlier, unit 0. We had, you know, all these parent functions, you know, this sort of thing, all these parent functions that we had, and now we've got two new ones. Well, no big whoop, I hope. Hopefully you recognize that this isn't in the regular graphable form, that this 0.5 is usually outside of the bracket. So I'm going to notice this to factor first, so then I can write it in graphable form. That 3 is outside. And now I can see what the horizontal transformation is. I'm going to make square brackets here just so I can see what's going on. When I factor out a 0.5, that's like dividing by 2. And so opposite operation, multiplying by 2. And notice when if I were to go back in the opposite order and expand this back out, yeah, I get a 3 there. And now I can hopefully see all the transformations. This is outside affecting y values. This is a vertical expansion by a factor of 3. This is horizontal. And you think multiplying by a half would squish it, but it stretches it, right? Because it's opposite when it's in with the x. Horizontal expansion by a factor of 2, which is, a half. 1 over a half is by a factor of 2. And here, opposite in the direction of x is left 6. And so notice that this this is the original function with all these transformations done to it. Now I'm going to pause the video and get my graph set up. You should do the same, I suppose, and then see if you can come up with the sketch. I'm going to pause just so I can get my graph going. All right, there's my grid. Boom, there it is. Just appeared from nowhere in the video, it looks like, but no, there it is. Notice the original graph. Why not do it? And it's parabola shaped. And notice that on the way I've done my scale, my next point at 2 would be up at 16. So it goes up really fast, right? And the idea of what does the shape look like, it's going to be like a boxy parabola. And as long as you do that boxy parabola shape with these 3 nice points, then we're golden. And now we're going to do the transformations in the order that we're used to. See, the idea of the factoring allowed us to do stretches and squishes first, right? Stretches first, and then I'm going to move my left 6. So a vertical expansion by a factor of 3. All the vertical distances get multiplied by a factor of 3. Vertical distances by a factor of 3. And notice that's true for all of them. So I'm going to draw a nice big fat point there. And notice that this purple graph isn't my final graph. But what's its equation? Well, it's only had the vertical expansion. That's this function. And then next I'm going to do my horizontal expansion. My horizontal expansion is everything horizontally gets multiplied by a factor of 2. So all of these distances get doubled. Well, the only nice points that I have are that one right there. So it goes from being 1 unit away to 2 units away. And I show my nice big fat points so I know what's going on. And notice that even though my sketch isn't very good, all of the vertical or horizontal distances get doubled. So if that's 1 and a little bit, well, this is going to be 2 and a little bit more. If I wanted to do some more points, I could do that. But I'm okay with this. Got my nice points there. 3 nice points. And what's the equation of this blue graph? Well, it's not done yet, but I can see it's 3 times a half x to the exponent 4. Dandy. And I've got my 3 nice points. Now I'm going to move everything left 6 units. Left 6. So all of these points get moved left 6 units. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and there's my transform graph. I hope this isn't a mystery to you, but what's the new thing about this is that we've got 2 new parent functions. That's all. This is review of last chapter stuff, isn't it? X plus 6 all to the exponent 4. So hopefully that's no big trouble. The last example we'll see is a little bit of calculator work, but that will come up in video 2.